Well, I'd first like to start by acknowledging the co-authors. This is some of the work that I'm presenting today was done, it was a group effort. So I'd like to acknowledge Luke Peters, Oka Badalan, Saskia Norchin, and Tana Velterop. As Nick mentioned, I'll be talking about how many ways are there to make a water table map, a review of data input and interpolation methodologies, including their associated errors. So this is work that I did mostly as a part of a postdoc, which was a collaboration between Flinders University and CSIRO. And part of this work, we actually did a review paper. So we did a review and we looked into water table mapping. And so a lot of this work that I'm presenting is part of that review, but then there's been a few other studies where we've looked at various aspects of water table mapping as well that's sort of combined with this. I'll start by asking, what is a water table map? I imagine that most people on this call can answer this question pretty easily. That's why you're here. But just to reiterate, a water table map is some sort of pictorial depiction of the level of the water table as a height or a depth beneath the ground. These are often one of the first things we do as hydrogeologists to try and understand an area. They're really foundational, fundamental tools in hydrogeology. They're really useful. They allow us to visualize horizontal flow directions and just to generally manage groundwater systems. So here we are specifically referring to unconfined systems, although some of the lessons in water table mapping are applicable to more general potentiometric surface mapping. But here I am referring mostly to the water table, which, just to recall, is the point under the ground where we are changing from a partially saturated or an unsaturated ground to being fully saturated. That's the point of the water table that we are trying to map. So you might be sitting here thinking, why are we talking about water table mapping? I know it, I get it, I've done it a million times. So one of my colleagues, Oka Badalan, was part of this study where they actually investigated what we think is the world's first water table map, which was done in 1856 in Liège, Belgium. And so we've been doing water table mapping for, almost 200 years. But despite this, there's actually minimal guidance on how to make one. There's also a lot of new data sets that exist. We're in the age of big data. We're collecting things with our drones and our satellites and our geophysics and our phones. And we can utilize this data to make our water table map better. But how do we actually do this? There's also been really a rise probably in numerical groundwater modeling, where we do numerical groundwater models now with almost like all of our sort of groundwater studies. And so partially we might start questioning whether the water table maps, which are generally not physically based, still have a role to play, in contemporary hydrogeology problems. Another reason this topic requires new consideration is the rise in coding in hydrogeology and the easy access to things like artificial intelligence and machine learning. This means that we can make water table maps really rapidly, but we might not necessarily understand the implications of what they mean when they're made using these kind of codes. There's also an increasing need for transparent data provenance and repeatability in methodologies for social and policy purposes. Today, I'm going to mostly focus on this first question. So how many ways are there to make a water table map? Just to burst your bubble, sorry, I won't answer this exactly. It's more of a general rhetorical question. And I'll be focusing on the plethora of data that we can use to make water table maps, as well as the variability in interpolation types. Throughout the presentation, I'll really be focusing on errors and uncertainty in water table mapping. And then at the end, I'll like to kind of summarize by talking about what makes a good water table map and some future directions for the industry and the research problem. Just to start with, very basically, very generally, we think about what the steps are for building a water table map. I mean, I've talked already about, we need to input data and then there's interpolation and things like that. But we think about that very first step, it's defining a purpose. It's really important that the purpose of the map, of the water table map, is defined and understood by, the client, if you're working with a client or with the team that's making the map. In our review, we identified 5 main categories of water table map purposes. These include flow, flux, and storage calculations. So generally, groundwater flows perpendicular to the contours of equal pressure or equal hydraulic head. And so we can use our water table maps to tell us where groundwater is flowing. If we know something about the aquifer properties, we can start to infer something about the flux. And then if we have information about change in water table maps through time, that's when we start to get information about storage properties. Water table maps are very useful for understanding ecosystem processes, things like groundwater dependent ecosystems, where they might be, how they might be functioning. Water table maps are very useful for groundwater system conceptualization, where the recharge areas, discharge areas, stream, surface water, groundwater connectivity, etc. They can also be used for hydraulic parameter estimation, like an inverse approach. We can use water table maps to start to try and tell us something about the physical properties of the system. And then also they're extremely relevant for management and monitoring of groundwater systems, and they've been used widely for monitoring network design. So it's really important to relate the purpose of this map to all of the elements of the water table. So if you think about how to make a map, sorry, I just heard something. That's okay. I can't see you guys, so if anything comes up, just interrupt me. It's important to relate the purpose to all the elements of how we make that map. One really good example of this is what the final map, how it's actually presented. What information are we actually presenting when we present a water table map? An example of this is that we can present a map as a surface above a reference datum or water level height. We can also present it as a depth to water table. And whether or not which one we choose will depend on that purpose. Generally, for most of our studies, we use a surface or a height of the water table. For contaminant transport, this is often used, or to understand flow directions. But depth to water table maps are extremely beneficial, particularly for ecosystem understanding, also for understanding, depth to drilling or flooding risks, or even for urban type projects. The purpose of the map will also guide factors such as, how big is the map going to be? How much time and resources can we actually invest in producing this map? And also how it's communicated and reported. Now I'd like to talk to you about the data inputs that are used to make water table maps. As we all know, the water table is generally completely hidden at the surface. So the most direct measurement of the water table is from point source measurements at groundwater wells or bores, as we all know. So there are lots of different ways of using groundwater wells to measure the water table. The most common being a simple measuring tape or a dipper. We also use automated loggers regularly. There's other vibrating wire sensors or laser-based techniques. And there have been some recent reviews on different methods for measuring the water table and some of the errors in these types of measurement. Some of the sources of error in this direct measurement of the water table include equipment or human failure, well construction, aquifer properties, and the timing of the measurement. And I'll talk about these a little bit more now. So if we think about when we're measuring the hydraulic head or the water table height equated to hydraulic head down the well using, say, like a measuring tape. We think about the case of A. We can have a depth, so a standing water level, where we're measuring with this little grey rectangle is the screen, the well screen. We can have a depth where we can get a very accurate estimate of the hydraulic head, where we have no measurement error, no conversion error, and a well constructed bore. That's great. However, the case of B shows you could have a depth that you're measuring to the water table, a standing water level, that's different from the hydraulic head. This could be due to human error. For example, you've misread the measuring tape, could be due to logger failure or stretched measurement tape or something like that. There's also a third case where you can have measurement error due to variation in the properties of the water. So this is where your measurement of the depth to the water table doesn't equate to hydraulic head because of factors such as like high salt content or high temperature, for example. You can also have error in your measurement of hydraulic head due to the well construction. So something we don't often think about that much is that to accurately measure the water table, the well should technically have a short screen across the water table, as you can see in A. And we know from practical purposes, this is rarely the case because it's expensive to drill wells and, usually we're drilling them for another purpose, say to maximize pumping yield. So in the cases where the screen, which is shown in gray, is, let's say it's an open bore as in B, or the screen sort of at the base of the well as in C, the measurement that you're receiving about the hydraulic head is actually not at the point of the water table. And what this means is it might be slightly different, particularly in areas with strong vertical gradients, such as recharge or discharge areas. It could also be different in cases such as D, where you have a partially confined aquifer system, or definitely in cases like E, where you have a perched aquifer. And then there are complications with kind of wells that aren't constructed, if they're not completely plumb, if they have some sort of dip, or there's other well construction issues as well. When I talk about this topic of water table mapping, something that comes up quite frequently is like, okay, I want to make a water table map of this area, but what data do I use? We often have to rely on like state or national data sets of water level data, where data is available often across many decades. We might have time series data, or we might just have single data points through time, and we have to make decisions about which data we aggregate, which data we use to make that map, because our map is only going to represent a single time period. So one thing we suggest is actually, if possible, to plot the data through time and to look at the trends that exist. Your data could be non-stationary and low variability, as is A. It could be non-stationary and high variability, as is B. It could be stationary and low variability, as is C. Or it could be stationary and high variability, for example, as is D. And in each of these cases, I would make kind of different assumptions about which data I'm actually going to use when I choose to make the water table map, when I'm aggregating this data. So for example, if you have non-stationary data, you might only average the period from, say, the last 5 years, whereas it might be more acceptable to kind of use all of the data and do some sort of average or aggregation in the case where you have a very non-stationary system. You should also assess your data for seasonality. And so when you choose how to aggregate the data, there's also questions about, how are you going to generate the mean? Are you using geometric or arithmetic, or use a median, or are you going to do some sort of outlier removal? When you're choosing the time period, if there is seasonality, maybe it's not as simple as choosing just a bulk year. Maybe you'll average over the past 10 years, but you'll just choose every data from June, for example, or from the dry season if you're working in the north, or if you're working in an agricultural area, maybe you'll average data over multiple years, but you'll only average after, irrigation has ended, or something like that. So we need to, it's nuanced how we use and choose data, but it does add error and uncertainty in our estimates and our production of that water table map. So if we think about this direct data or these hydraulic head measurements, we can think about there being like a true quantity of interest that we want, which is represented by this thick black line. That's our true water table level, but that is bound by some error. When we look at our observation, which is this H with the O, what we're observing is that we are observing the true water table level, but it's got some error associated with it. So we could think about this as a very simple equation. We can say, okay, the hydraulic head is what we're interested in, but what we can actually measure, there's some sort of measurement error associated with that. However, we really don't want to just limit ourselves at using direct data as much as possible. So point source data is great. It gives us the most direct measurement of the water table, but it often doesn't have very good spatial coverage. So in addition to using that, as much as possible, we should think about outside the box. We could use additional data sets such as topographic data or conceptual information. We might also use measurements from satellite or geophysics. However, considerable uncertainty exists in knowing how to integrate these direct and indirect forms of measurement. So one first step that we suggest is to actually think about categorizing the data that you have and categorizing it based on the relationship that that data has with the water table. So we already talked about direct data, but the second category we introduce is proxy data. And in this case, proxy data are data where the water table controls the signal that you're measuring. The best example of this is geophysics. Here we have an image of surface nuclear magnetic resonance, where what you're measuring is the excitation of some neutrons underground. And that is a function of that water table, the physical properties of the water table. The second or the third category of data are known as covariate data. And in this case, it's just flipped around. It's just the opposite. The signal that you're measuring controls the water table. So the best example of this are digital elevation models or topography. Now, we all know that in many cases, the water table is a subdued replica of the topographic system. And that means that we can use what we know about topography to map the water table. So if there's a slope on the ground, it's not there because of the water table. It's the other way around. That slope on the ground is likely to control some sort of slope in the water table. So the relationship between the data and the water table is just the opposite for covariate data that it is for proxy data. So again, when we think about what we're actually measuring, if we go back to that topographic data with our covariate data, what we want to know is the land surface at a point, because that can tell us information about the water table. But what we can actually observe is something close to that land surface. There is, again, this kind of measurement uncertainty associated with that. So I won't go through this in a lot of detail, but just remembering again that even with the covariate and the proxy data, the data that we're measuring has some sort of wobble. It has some sort of error, measurement error associated with it. And that we've called this first error term, which is associated with the data signal measurement. When we're out there and we're collecting data that we're using to make a water table map, it's important, of course, to think about the system that we're in and how that data can be used to map the water table, because it's going to be different for every different system. So for example, if we're using a drone to collect topographic data, this can inform the water table. It's a covariate data, it's a covariate signal. However, we really need to know how the topography and the water table are related for this system. This will depend on factors such as the recharge rate, transmissivity, hydrological boundaries, etc. And there's a great paper on that. So just because in one area you have a really strong relation between the water table and the topography, it doesn't mean you will necessarily have the exact same relationship in another part of Australia or the world. Similarly, we're collecting some ground-based electromagnetics. This can inform the water table for our area. However, we need to know how the electromagnetics and the water table are related for this system. And that could depend on factors such as aquifer salinity, clay content, etc. Again, it's system dependent. So unfortunately, that adds just this extra level of kind of complexity when we're using proxy and covariate data. We can think about this as the there's some sort of conversion. We need to convert that raw signal that we're collecting into a prediction of the water table. And that requires knowledge of the conceptual model of the site. So the formula gets a little bit more complicated, but bear with me. We have some true hydraulic head that we want to know at a point. This is a function of, so we didn't have that before with the direct data, but now the true hydraulic head is a function of what we're actually measuring. So our covariate or our proxy data. But now there's an additional second error term used, and that's our conversion. That's where we're saying, okay, like I've got this electromagnetic data and it's showing low resistivity at this depth. Okay, what does that mean for my site and for my water table prediction? So the second-error term is associated with the conversion of the measured data to the water table. So what kind of data can we use for water table mapping? There are a lot, actually. And on this slide, I've just included probably the most commonly used data, and I've separated them based on the type here. So for our direct data, as I mentioned, we can use hydraulic head. We can also use surface water stage, where the system is highly connected. Covariate data, the most commonly used covariate data are topographic data. We can also use morphometric variables, which are actually derivatives of topographic data that include things like slope or drainage networks. We can use conceptual aquifer features, like what we know about the geology. Is there a fault? Where is there a discharge feature, for example? Even climate information could be used. Proxy data sets, the most common is, geophysical data sets, but also could be remote sensing. There's a real challenge around data knowledge interdependencies. And again, this comes back to the importance of kind of defining that relation between the data that you're using and the water table. So a really good example of this is when we use surface water stage data to map the water table. And in a study looking at groundwater surface water connectivity in the Murray-Darling Basin, I think they summarized this really well. So basically, the study had to make assumptions about the connectivity status between the river and the groundwater. And then those assumptions were used and embedded to make the water level map. So they said, okay, everything's connected. It's all connected. Now we're going to make a water level map. And then that water level map, or that water table map, was used to understand what, or predict what the water level adjacent to the streams would be. And then that was then further used to inform the connectivity status of the system. It's a little bit chicken and egg sometimes, where we need the information from the water table map to know what's happening in the system, but then we kind of need to know what's happening in the system to make the water table map. It can be a real challenge. Now I'm going to still talk to you about making a water table map, but we're going to talk about types of interpolation. So as I mentioned, our primary or our most direct form of data come from point source measurements at wells. And then often, if we're lucky, we have these proxy and covariate data sets that might have much better coverage. But in general, we have more space in a system where we don't know what the water table is than what we do know what the water table is. There's a large paucity or there's large uncertainty due to absence of data in between our measurement points or our known points. And so when I talk about interpolation, I'm just talking about predicting what the water table is at a point where we don't have information based on the information that we do have around it. There are lots of options for data interpolation used for water table mapping. So these range in the quite dramatically in how the data are used and integrated. They range from hand-drawn water table mapping, deterministic approaches, linear geostatistics, also known as kriging, which is one of the most commonly used methods. Non-linear geostatistics, usually Bayesian type approaches. You can have physically based models or numerical models, but I won't talk about these a lot today. Regression analyses, and then these move into data-driven approaches such as machine learning. So I'm not here to tell you that there is one method that is superior to another. The right methodology will depend on the study, purpose, the practitioner, what they're comfortable with doing, what they know how to do. Comparing between methodologies can be really complex, in fact. So I've just have some different nice images of water table maps now with some of the different interpolation methodologies that we use to produce them. And I think that I like this because it just shows that there's just such a range of kind of visual presentation of water table maps, as well as the method behind it. And it's not necessarily obvious or linear, in fact, in time, how these methods have changed. So, for example, yes, in the past, and the first water table map was done using hand-drawn approach, but it's not been some linear transition where we've all changed from hand-drawn to kriging to something else to machine learning. No, in fact, kriging is still very commonly used, and And machine learning is becoming more common now, but it's certainly not ubiquitous or widespread. And in fact, I was working at Geoscience Australia in 2012 when this really lovely work by the great late hydrogeologist Jim Kellett was done, where he actually used hand-drawn technique for mapping large parts of the Great Artesian Basin, and that work is still used today. So there are many different methods, and there's a sort of a probably limited guidance on which method to use at which time and which method is necessarily the best method for the study that you're working on. But hand-drawn mapping is still used today, as I said, and we decided to kind of probe or investigate this a little bit further because it's quite interesting really that hand-drawn technique is still used widely within the industry. And it's interesting because there has been, we're like advancing so quickly with this AI and machine learning, but then yet we're still going back to drawing things with a pencil and paper. So it's like, hang on, wait, why are we doing this? And we sort of suggest that there are two main reasons for this. And the first one is that there are limited techniques, there are limited automated techniques that allow for the flexibility in incorporating multiple data sets. So, if you know there's a fault somewhere, you know where a recharge zone is, you have some information about topography, how do you put them all together? Well, you not only want to do that, but you also want your map to satisfy what you think it should look like. And that can be really challenging. Additionally, some of the more flexible techniques that can incorporate multiple data sets, they often require skill and resources that might be above the current capability of people that want to make water table maps. They might require quite a lot of coding or investment in method development. So we did an experiment where we actually asked participants to draw a water table map for us. And the region was for the Willunga Sub-Basin, which is just south of Adelaide. We had 63 participants join in this study. And if any of you who are listening did do this study for us, we'd like to really sincerely thank you because the research has been really illuminating and we appreciate the time that you put in. So participants were from a variety of backgrounds, including industry, academia, and government. And they were mostly from Australia, but some from overseas as well. This was the map that we used for the study. As you can see, participants were given points, or they were asked to draw for this area shown in thick black line. And then they were given points that represent the water table height. We said, it represents it perfectly, basically. So that's the hydraulic head at the water table. And they were also given information about the stream network, topographic contours, which are shown in gold, and a geological fault, which is represented by this dashed line. They were asked to draw contours and then follow up with a questionnaire, which they could access via a QR code on the map. So the method basically was participants provided their input with a pen and a paper. We scanned those maps, digitized them, output the data as rasters, and then we used Python to kind of analyze the difference between the maps and to make some summary statistics. The questionnaire accompanying the mapping exercise was really interesting. We asked people about their background, as the background of the participants. We asked them about their preferences for water table mapping, their approach to the exercise, such as where did they struggle to draw contours. And then also we asked them to predict the water level height on the map at particular locations, which were indicated with a letter, so a point with a letter. And this was used to look at how good the maps are for kind of predicting, extrapolating or predicting outside the known data points. Some of the results from the survey are shown on the right. And in the blue bar graph, you can see we found that the preferred techniques for water table mapping was linear geostatistics, or also known as kriging, which we expected because in most studies that you read about, linear geostatistics is used. But the second most popular was a manual or a hand-drawn approach, which was quite interesting that it is still certainly relevant today. And the usual platform for water table mapping was tied between, GIS platforms and also hand-drawn approaches. When we look at the results of this study and we aggregate them all together and we create like a mean water table, we can see that the results really did reflect what we knew about the water table conditions for the area. And when we look at the fit at each point, so each known point of hydraulic head, the sort of calibration statistics were really acceptable. So it resulted in overall, really good quality, useful maps. The variability between participants was largely concentrated across that pesky fault and in areas of high changes in topographic slope, in areas with low data density, and where there was sort of spurious input data where something wasn't quite right. Maybe 2 points near each other didn't match very well. And that's shown on the right here in this map of standard deviation across the region. If we break it apart though, and we start to look at each individual map, what we could see was quite a lot of variability in the style of the water table mapping. And we've kind of divided it up into 4 types approximately, which are shown here. And you can see that the style varied due to the way that the fault was represented, how contours were drawn across the fault, also how bullseyes were used to fit, spurious data points, as well as, how straight were the lines versus how intricate were they. Some people's lines were very intricate. They followed topography, followed valleys very clearly. And for other people, it was, they were a little bit more, I suppose, parsimonious. So it's useful to think about this workflow, and think about why people are doing hand-drawn water table maps when we compare it to automated techniques. So if we think about now an automated interpolation workflow, which is shown on the slide now, what we can think about is that we get some data inputs. So we have our direct data, we've got our wells, we've also might have some other data. We then have an interpolation model. This is some sort of mathematical model. We could be using, geostatistics, regression analyses, machine learning, it doesn't matter. The fit of this model is determined by fit metrics, which are generally looking at best fit at our known data points using something like root mean square error. And that results in our final map. However, when we do hand-drawn water table mapping, we're no longer using a mathematical model to fit data, to combine, interpolate data. We're using a cognitive model that's based on a practitioner's training and experience. And instead of fit metrics, we're relying on intuition. Does this look right based on expectations that are driven by what they know about the physics of a system? And so there are many benefits of automated interpolation, like repeatability and transparency, speed, and also accuracy of fitting known measurements, if that's important to you. But there are limitations, and one of that is that there's lack of integration with a known conceptual model. So it can be really challenging to with your automated technique to know that something doesn't look right. And often what happens is, particularly with kriging, we have really good fit at points. You get a lot of bullseyes, right? So as a hydrogeologist, you think, well, hang on, there shouldn't be a pumping well or a recharge feature there. So what's going on? How do I fix this? How do I make it fit with what I know to be happening in this system? And there's also the inability to account for unconventional data types. So the human is able to go, okay, I know there's a fault. I know what's going on with this fault. Something wacky is going on with these contours. But a computer might have a lot more challenges, or we as humans might have challenges telling the computer how to use that fault in order to, reconfigure a water table map. When we're thinking about the automated water table interpolation process, we can think about using our direct data, our proxy data, for example, our geophysical survey, and our covariate data. These might be kind of spatially configured at different points around the domain. And then we want to know, how do we actually use these data to predict the water table for this whole region, when, as we've talked about, they have errors associated with them. and they're system dependent. It can be quite complex. So now we have an even more messy formula, but just again, bear with me. So what we're looking at now is, again, we want to have some sort of prediction of the hydraulic head at all spatial locations in the domain. This is just what is the hydraulic head? What is the true water table at that point? This is now a function of all of those different data types. The blue are the direct data, where we have the direct data at every single point that we have a direct data measurement, plus the measurement errors associated with it. Then we have our covariate data at every point. We've got the measurement uncertainty, plus we've got that extra conversion uncertainty, and the same with the proxy data. We also have our spatial location, because that's really important in our interpolation algorithms. So we have an X and a Y. And then we have some sort of interpolation error as well on top of this, because the way that we're combining these and the model that we're actually using to combine these has an additional third type of error. This is an error that's associated with the interpolation function itself. So I'm not going to go through these in too much detail, because there's a lot of different approaches and each of them kind of has its own issues with uncertainty. But if we think about two of the most common ones, we have our hand-drawn mapping, and probably one of the key errors in hand-drawn mapping is that bias in our human cognitive model, which is going to vary between people. We think about our linear geostatistics or our Kriging. There's uncertainty in the variogram model that's actually used to combine the data. And I know a lot of us who do linear geostatistics, we might use a platform such as ArcGIS, and it's very easy to kind of pop your data in and say, yes, 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 water table map, good, done, bang. And I'd like question you to say, like, okay, what is a variogram? And I can tell you that I couldn't have answered that question very well before I did this research. Variograms are quite complex, and but yet the way that they're set up and the model that we choose to use could really widely affect the map that we finally produce. So that's part of the question of going, okay, hang on, what variogram have I used and what does that mean for my interpolation? What we can also see from this table is that we have for each different technique in this second column, we have, how flexible are they in terms of their ability to use these covariate and proxy data sets. And so some of the more simple approaches, it's very difficult to add non-conventional data sets in, but as the techniques maybe get a little bit more complicated, it is the ability to then use non-conventional data sets becomes easier. So when we think about uncertainty analysis for water table mapping, you might just say, like, what uncertainty analysis? Because most water table maps don't have any form of uncertainty analysis. Yet we've shown that there are 3 types of error in the measurement of the data, in converting data to an estimate of water table, and then also in combining and interpolating these data to predict water level across the region. So I'd like to advocate that as a community, we need to start to think of methods to propagate these errors and consider uncertainty in water table mapping, even though they're not currently widespread. There is often, when we use Kriging or linear geostatistics, your Krieged mean estimate of water table is often accompanied by an estimate of the variance. However, this is really a measure of data density, and it doesn't go any way to sort of pull apart or think about those errors that we've already discussed. I already mentioned there are some limitations of using goodness of fit to fit data. So again, that's where we're saying, okay, look, we've fit our point really, really well, but we need to think beyond this and think not just about fitting a point, but fitting some sort of conceptual model. Does the flow direction look right? Are our recharge areas in the right place, for example? There have been some really cool studies recently where people are starting to think about water table maps in a more probabilistic way and thinking about presenting them not as a single map, but rather some sort of ensemble or probabilistic depiction of water level maps. And this is like, we're seeing this go in leaps and bounds in the kind of numerical modeling space, but we're not seeing very much of it at all in the water table mapping space. Sorry. Okay. So just finally, I'd like to talk about what makes a good water table map, because I've kind of jumped through a lot of nitty-gritty and a lot of pedantic aspects of all the different areas and all the different data and all the different interpolation methods. But when it comes down to it, the really important thing to talk about is not that you have to quantify every aspect of error and it has to be perfect and it needs to be this big complicated ensemble. It's actually that we're just thinking about these and we're starting to communicate them and starting to report them as much as possible. So it's not the interpolation type itself that makes the map good, it's the way it's used and communicated. So elements of a good water table map include, again, a description of that purpose and what assumptions have gone into making your map. How did you classify the input data? What did you do to pre-process it? Did you remove outliers? What time period was the data used for? And then think about the limitations of if you're using proxy and covariate data, how does that relate to the water table for your site? And then also of your chosen interpolation methodology. So thinking about that variogram model or, what other methodology you've used, are there some, are there some base assumptions that you made? And think about, some strategy for communicating that. So in conclusion, there are many ways to make a water table map. The best method depends on the purpose, available data, and the practitioner background. So there's not just one key, one map fits all. Novel data sets should be embraced, but it's really helpful to define that relationship between the data set and the water table, and whether it's a direct one, a proxy one, or a covariate one. There are 3 types of errors in making water table map, and we're not advocating that these are like explicitly quantified, but they should be considered as best as possible and communicated. Each interpolation method has pros and cons, and we can have more flexible methodologies, but they become more complex. So look, some of the most basic water table maps still have a place. Reporting the maps is critical, and we should be starting to consider uncertainty analysis in the form of ensembles where possible. I won't go through these just now because they're actually sort of just expansions on the conclusions, but I'll leave them up on the screen in a minute. And with that, I'll just say thank you for this opportunity to present our research. I really appreciate it. Yeah, happy to have any questions. Thank you.
Sarah, thank you so much. It's quite refreshing to see such a strong presentation on physical hydrogeology once again, going back to our first principles. And I will say that I've been keeping an eye on the number of people that have been in the room, and Larissa Cullen, it looks like there's 8 people in their room and we've got 17 here. So I think we had over 81 people on the call at the most, which is probably over 1/4 of all of the hydrogeologists in Australia. So I think this is a record attendance, at least for us here in Queensland. So we'll applaud your talk as being a very, very interested one to many professionals. So thank you. Yeah, and that's excluding everyone who will watch the recording.
Oh, so thank you. The topic, so, yeah, it's certainly
another righty.
So does anyone in the room, any of the rooms or online have any questions? I know and there's not all from Australia. I believe Vladislav is from out of the country as well. So you've got an international audience here as well.
Oh, wow. Thank you.
Do we have any questions for Sarah at this point? Either in the room or online? Not all at once.
Got a comment. So
we're having technical difficulties in the room.
Hey Sarah, I've come to Queensland.
Oh, hey, nice. Oh, nice to see you.
So you talked about different reasons for doing things different ways.
Yeah.
Can you maybe provide a comment on the time required to use different methods?
Yeah. Look, there is research going in the background. People like our team and others who are maybe trying to make some of the more flexible, maybe slightly more, I guess, the approaches that don't currently have some sort of GUI or some sort of very accessible platform for using them. For example, like the non-linear geostatistics or, you know, the machine learning and things like that. So people are working on them, trying to make them more accessible and to try and communicate and work on workflows for integrating data. So that's kind of like still in the work in progress state. I'd say the time, it's really interesting. I gave a different part of this talk at ModSim conference earlier this year. And one of the people in the audience was Stephen Gorelick, who I know has been in Queensland and probably a lot of you know, and he's a Stanford professor. So I felt like whatever he says, you know, I'll just trust and believe. And he just said, it just has to be hand drawn. You know, he was just, well, I won't, you know, completely paraphrase him, but he was saying that's the way he teaches all his students. And that's, you know, that's what he will do generally for a region, is that he will use a hand drawn method, because at the moment, unfortunately, as much as we're trying to catch up, just nothing exists that's quite as flexible. And so a hand-drawn approach, hopefully all of us, like in terms of time to learn it, that's the stuff that we are kind of learning at hydrogeology at university and kind of coming out and then just refining through our careers. When it comes to some of those more machine learning and the ones that require like a coding, so I guess that just depends on, you know, your background with either using coding or whether using even ArcGIS and things like that. But yeah, there is a broad spectrum. You can make a water table map in an hour if you want, but is it going to be useful? That's the question.
Sounds good. I'm going to ask two of the questions that have been populated in the line, then I'll open it up to more in the room. You are becoming quite popular. So we have Jason Pinza. He says, nice presentation. How do you include uncertainty in your communication, for instance, to stakeholders from your experience?
Yeah, and that's something that we are working on, actually getting some guidance out. My colleague Saskia Nugent is working on a paper about actually like the workflow of water table mapping. And we have had so many discussions where we go quite technical and then we end up coming back to reporting and thinking that it's probably the most important aspect of water table mapping. Communicating uncertainty is a real challenge, and I know that those working in the numerical modelling space have been grappling and facing this, and in fact doing a really good job. I think that the most important thing is just documenting the methodology and the data and the assumptions. So some of those pre-processing steps, you know, I think the number of times you read a map with a water level data, but you don't know when that data point was taken, or, you know, was it an average, or was it a is there one data point? At what time are you actually, what time is the map presenting? Is it like 2021 or was it 2010 or something? So I think that it's about really just trying as much as possible to report what you've done in your method. I don't think at this stage there's no way we could advocate that every method needs a quantitative assessment of uncertainty, but it's about starting to just report what you did use, how much variability. For example, if you have time series data, plot it up, you know, this is what we had and this is the data that we used. This was the range. We used this variogram model, but, you know, actually we've tested some other ones. And one thing we say with hand-drawn mapping is maybe get your mate to do it, get your colleague to do it as well, and just have a look at how different they are. Where are they different? You know, maybe that could help you to explain the variability. And just one other thing, there's something called a mapping reliability diagram as well. So, you know, presenting your map, but you could also just present a map showing where are the data points. You know, you could use some sort of color scale to show, okay, well, we didn't actually really know what was going on over here, but over here, we really know what's going on. So you can do it in visual ways as well.
Perfect, thank you. So there's a comment here saying, in areas with deep water table and dipping geology, it can be useful to look at the geology at the water table when reviewing water table maps. Geology at depth may be different than geology at the surface. So I think that's reinforcing some of the need for, yeah, the traditional geological approaches. I'll ask one more question online and then I'll open it up to the room here. So Pankaj Kaushik says, great talk. I think that's a common theme. Do you think that traditional methods of measuring the water table should be validated with machine learning or other techniques, especially in places such as the Great Artesian Basin that are more complex?
Oh, I don't know about validation with machine learning in one sentence, if that's possible. I would think of validation as being with, with more field data. But let me try and think of what you're trying to say.
Maybe it's testing alternative hypotheses to confirm.
Yeah, so I think that uncertainty, it's funny because we've talked a lot about pedantry, like that first slide where I talk about kind of the uncertainty or the error that can be associated in hydraulic head measurements. One of the papers that I referenced on that slide, the Rao et al., they've done a really good job at actually going down into that nitty gritty and thinking about all the different sources and magnitudes of error. But some of them will be very minor, particularly if it's like a measuring table, like the person might be, we're pretty good, right? Maybe we're just off by a few millimeters or something like that. And in a Great Artesian Basin, a few millimeters might not have all that much of a problem. But I think that exploring the data and the variability that could exist in interpolation with any kind of interpolation approach, whether it's machine learning or something like linear geostatistics, is a very good idea. But always important to think back to basics and present the data itself on its own, and to think about it. Also, just do some really simple, common sense checks. So if you're using machine learning, maybe just quickly draw a water table map as well on your own, or use another method and compare if you have time.
Fantastic, thank you. So we've got 2 more questions in the room and we will limit it to the 3 questions that are online. And then I'd invite, if anyone does have any further questions, just to leave them in the chat. And if you're very kind to Sarah, she may respond afterwards. But I'll pass it over to the 2 questions in the room, and then I'll address the 3 questions online, and we'll conclude it then.
Thanks a lot for the talk. It's really, really interesting. So a quick question is, in the test case you presented, and I guess you've had time to look at the results and maybe test automatic interpolators there. Have you found any automatic interpolation method that somewhat resembles what people did by hand? So I wonder if there's anything flexible enough that incorporates topo, that checks depth to water, that you don't get water flying off the ground, that incorporates drainages, that incorporates as many things as we can. What would be the nicest automatic interpolator in based on what you've learned?
Yeah, so we have been exploring, and my colleague Saskia Norchin, hi Eamon, by the way, we work together, has been exploring the methods for automated interpolation for this site. And I just spoke to her a few days ago, and she said it's funny, she's finding the one of the best ways is actually to stitch together a few different methods at different parts of the domain. So for example, where the system's very flat, it's useful to use something. So there's a whole family of kriging, and if you haven't explored it, you might not know, but I mean, there's one kriging technique for like the flat part, and then a different kriging technique, for example, for the part where the topography really changes. And that's not really ideal, right? To have to kind of stitch together like 2 different algorithms. It's certainly something that you can program, and it's not impossible. In terms of including drainages and faults and things like that, there's been some really good work that's done in the space of nonlinear geostatistics. So the kind of Bayesian data fusion is one of the options, and that just allows for a much more flexible incorporation of that conceptual information. Whereas the linear geostatistics, you can include things like, you can pretty easily include slope, but for things that are non-continuous, like a fault or something like that, it does become a lot more challenging. So I suppose my answer is very broadly, we can use very simple sort of kriging to get something that looks okay, that looks fine, really reasonable. But to make it look, really good, it does start to get a little bit more challenging.
Hi, Sarah. Yeah, great talk. I guess my question kind of relates coming back to your start where you emphasised that when we make these maps, it's we're gonna have defined our purpose first, and like when we end up producing a map, or perhaps we're actually just seeing someone else having produced a map, we might be thinking, hey, we could use it for this or that, and maybe the purposes that we end up using these maps might not be the original purpose that it was designed for. Do you care to comment on any perils that may bring?
Yeah, that's a really good point. I think that, like, in the end, if it's done well, I might fight myself for saying this, but I'd say a water table map for a region is a water table map for a region. And it even though we strongly advocate defining the purpose from the outset, it doesn't mean that they're not going to be, adaptable for other reasons. A map that you're using to understand surface water, groundwater connectivity in the Murray-Darling Basin is probably also going to be very helpful for understanding things like salt transport and loads and things like that. But if you haven't defined that purpose, then it's really difficult to know the steps that you should take, because the purpose will define even things like how much resources you have to invest in that map itself. A contaminant transport problem is going to require a very different water table map from a much broader regional study. And we can emphasize different things when we are collating data. So if we're looking at a regional study, we might really want to emphasize really just understanding horizontal flow directions. And so it's really about that broad, like where's recharge happening, where's discharge happening, and using coastal features or using streams. But if it's about contaminant transport, it might need to be much more detailed for a particular region, and we might focus much more on, fitting data points, for example. So in one case, we might want to make sure we get horizontal flow directions right, and in another case, we might want to fit data really well and get lots of bullseyes and things like that, and it doesn't matter so much. So the overall map that you result in, they can be adaptable, but it is important to think about the purpose from the beginning.
Fantastic. So we'll limit it to 3 more questions, and there's 1 on the chat and 2 in the Q&A, and then we'll call it quits and take you off the hot seat. So the next one's from Michael Carroll, and it's any thoughts on a combination of methods? I think you may have answered part of that, but he said a simple example might be adding manual training data to guide interpolations. And I assume that might be like at surface water bodies or water courses, actually adding some of those data points. Did you have anything to comment on that?
Absolutely. I think that it definitely it's used widely. So like dummy point in automated interpolation. So really like a good example is, like you just mentioned, if you have a surface water system or a valley or some kind, it can be very difficult to pull the water table down to a level that you actually know it should be at that point. So you can add sort of these dummy points to allow you to do that. And I've seen some really cool novel approaches to do that. Obviously, people can do them by eye using what they know of a system, but there was a study in the Great Artesian Basin where they used NDVI to actually think about like greenest indices along a river, and then use that to add in dummy points, for example. I think that there've been studies where people have, done the automated interpolation and gone, oh, okay, these contours look wrong, I'm just going to change them. Some of the work in Nevada on the kind of nuclear waste disposal work in the US that was done for water table mapping, a combination of human and automated approaches. The challenge is going to be, as we move forward into politically sensitive or environmentally sensitive cases where we need to have methods that are, repeatable and transparent, we need to just make sure we explain what we did and and when we did it, and again having that in the reporting. But yeah, I think that that's the space that we're playing in at the moment. There don't really some methods that are automated and flexible. They're just not quite there yet. I think they probably will be in a few years' time. But yeah, at the moment, humans all for it.
Fantastic. We've got another question, second to last, from Jeff Pettifer, and it's, can you comment on the mapping spatial variability of reliability? Do you favor machine mapping or human interpretation?
Mapping
I think you
spatial.
might have already touched on that, but if you want to elaborate.
So I think that that's talking about reliability, mapping kind of reliability diagrams that I just talked about. I am, like, despite the fact that I'm advocating for hand-drawn mapping and, you know, us humans getting involved, I really am for automated approaches as much as possible, just because of their repeatability and transparency. I think it's really important, and I've worked predominantly in the government space. So, and also just for comparative purposes, you know, like when we want to compare things through time, it's useful if we have products that can be, you know, we know that they have exactly the same underlying assumptions and can be easily compared. So I would say the same for kind of mapping reliability diagrams. And the approach that I generally use is I do as much as I possibly can coding, or if it's not coding, then it's a sort of like a GIS workflow that's very clearly, the steps very clearly explained so that I can reproduce it again. And then you kind of get as far as you can, and then add on as a human, with, you know, I mean, don't look past things like how you're using colors, how you're using annotations, how you're using shading, because all of that is really important in the space, particularly of that reliability diagram. So yeah, I don't know if that answered that question very well.
Well, if it doesn't, I'm sure Jeff will reach out to you directly.
Yeah, and my email is provided, I think.
So the final question we will ask is from Michael Tubner, and he's online should he like to elaborate further, but or if you need clarification, but he's asking if you can provide some idea how to develop the variograms in question. So if you need further clarification, he's online and he can come off mute, but take it away.
Yeah, look, there is a lot in this space. So if you're familiar with coding, the best platform is definitely R for anything statistics and variogram related. Python is almost there. And look, a variogram in its essence, all that it's doing is it's looking at the relationship between points and data points. So like, let's say hydraulic head, and how similar they are at a distance from each other. So you say, okay, the data that are close to each other, the data that are within 10 meters are really similar, but as we spread out, as we get further and further away, they become less similar, and they get less similar to a point that we can just discard that data. Okay, if I'm in Adelaide, I'm probably not going to use data from Roma to make my water table map, but hey, I might use data from, I don't know, Wollonga or something like that. So it's just about how similar data are with distance. And so, at the very essence, you can just code that up. You can plot that up in Excel very simply. The challenge exists when you have lots of data, because your computer will explode. And so there's something called an experimental variogram, and that's what I'm talking about. We can just kind of plot it up, and then we generally fit that with a theoretical variogram. And the reason we do this is because when we use the variogram for our interpolation, if it doesn't fit certain rules of curvature and, you know, mathematical, you know, things, it will fail. The interpolation won't work. And so there's generally like specific types of variograms that are used. They're called spherical or Gaussian or things like that. And so it's the process of fitting your variogram that's where the challenges lie. And that's where there's a bit of, you know, you can either just use your settings that exist and go yes, 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 or you can try and make it a lot smoother, or you can make it like less smooth, or you can have more measurement uncertainty. That's something called the nugget. And look, I'd say that the best options are at this stage within R. even ArcGIS has very good geostatistics in terms of variogram modeling. I haven't got around using QGIS, so I'm not super across that, but I'd say it's probably similar. But the GIS platforms are very useful. But in terms of actually investigating that kind of uncertainty and what that means for like making ensembles and things like that, we're not quite there yet. There is some work, particularly in like the petroleum space, where they're always like ahead of us, right, with things like this. So there's more work in that space, but yeah, the modeling and of the theoretical variogram is still a little bit of a challenge, but R would be your best bet.
Well,
Thank
Sarah,
you.
thank you so very much. We will release you from your obligations going forward. If people have further questions, we'd invite them to reach out to you directly. But I would just like to thank you for taking the time to present to the national audience and international audience, but also to say that it's really quite refreshing to see someone so passionate about some of the physical, hydrogeological, and first principles. So thank you so very much for your talk. It was greatly appreciated. And as I said, you've reached out to probably the largest audience that we've had at the IH from Queensland of over 80 people. So thank you so very much and have the best day possible.
Okay, thanks so much. I really appreciate it. I'll yeah, just email me if any other questions kind of come up, but I really appreciate it. Hope everyone has a good night.
Yeah, I did see a lot of emails flying behind